Hello students, I welcome you all to the next lecture of the JC Connect series of online lecture. In today's lecture, we will be starting with the module 4, which is design for shear. In previous module, we have gone through the design for flexure, and now in this module we will be studying design of shear. Let us start with the definition of shear force. Shear force is defined as the force transverse to the beam at a section tending to shear at that section. Means a shear force is that force which acts along the surface and tries to shear off the surface along which it is acting. Now when we see at the figure below, there all the three forces, that is tensile, compressive and shear forces, are represented. When we see the tensile force, we observe that the forces acting on both the sides are trying to pull the element, whereas in case of compressive force, the forces acting are trying to compress or push the element, whereas when we see the shear force, both the forces are acting in opposite direction, which leads to the shearing of the surface. Now, understanding the design of shear force is not as easy as the design of flexural element. Then, modes of shear failure in pre-stress concrete beam. Generally in shear failure we have 5 modes, but here in our PSC beams we are applying only 2 modes, or we are trying to study only 2 modes, which are web shear cracking and flexure shear cracking. In the further videos, in the next videos, we will be going in depth with these concepts. Briefly, I like to tell that the web shear cracking is the cracking because of pure shear force. When the tensile forces increase the limiting capacity of concrete, they result in cracking, which in turn results in web shear. So this is a pure shear force without the effect of any bending, whereas the flexural shear cracking is the shear force induced because of the tension induced in concrete as a result of flexural or say bending action. So the shear force is not pure shear, but it is an shear induced because of bending. So these two modes of failure we will be dealing with in the further videos. Now let's understand the distribution of shear force. The effective shear area in a rectangular section is the one which is above the neutral axis. That means the shear force is causing much more damage in the top section, which is the compressive region. So while analyzing, we have to take the top half of the beam. Remember this point. Further, we have stress distribution because of flexure and shear. Then the shear stress. If you recall your RCC, we used to compute the shear stress tau V is equal to Vu divided by Bd, where Vu was the maximum shear force and Bd was nothing but the area of the section. But in case of PSC beams, we have the relationship tau V is equal to V into S divided by I into B, where tau V is the shearing stress due to the loads, V is the total shearing force, S is the statical moment or first moment of area, which is nothing but A into Y bar. Okay, which is nothing but A into Y bar, where A is the area under shear stress. So as explained in the previous diagram, this area is B into D by 2. Okay, this area is not B into D because we are taking the impact of shear force in the compressive region, which is above the neutral axis. This is B into D by 2. Then I is the second moment of area or moment of inertia. For rectangular element it is BD cube by 12, and if we have a I section we have to compute. Then next B is the breadth of the section at the given point. Now if we are analyzing a flanged section, B has to be taken as the width of the flange for a I section or a T section. So this formula is very important. In the first part of the problems we will be using this formula to find your tau v. Then let's come to the concept. Firstly, let us understand principal and direct stresses. Shear stress induces principal stresses F maximum and F minimum on the diagonal plane. Okay, so because of your shear stress, principal stresses, that is F max and F minimum, are induced along the diagonal. Shear stress is generally accompanied by direct stress Fx along the axial direction of the member, and if the member is subjected to vertical pre-stressing, we also get the direct stress Fy, which is acting perpendicular to the member axis. So these two forces also come into picture when we go to analyze the effect of shear in case of pre-stress concrete. Now, as Fx and Fy, which are the direct stresses, are compressive in nature, okay, they help in eliminating the risk of diagonal tension cracks in concrete. Now this is one advantage of PSC over RCC, that Fx and Fy, which are the induced stresses, they prevent the diagonal tension cracks in concrete. This advantage we don't have in RCC members. Hence we can say that PSC members can resist more amount of shear as compared to RCC members. Now this is the diagram about which we are talking, that is the shear diagram. So Fx and Fy are your direct stresses. Generally in case of beams it is rare that we have Fy. If it is asked or given, we have to use it because Fy comes with the vertical pre-stressing, whereas Fx is your horizontal pre-stress applied. It results in tau v, which is your shear stress, and along the diagonal we find your principal stresses F minimum and F maximum. So in the first analysis examples we will have to find these stresses, that is F minimum and F maximum. The formula for finding the maximum and minimum pre-stress principal stress goes like this: F maximum or minimum is equal to Fx plus Fy divided by 2 plus or minus half into square root of Fx minus Fy the whole square plus 4 times tau v square, where Fx and Fy are the direct stresses and tau v is the shear stress. So using this relationship we will have to find maximum and minimum principal stresses. Okay, so in today's lecture we have discussed about what is a shear force. When a shear force acts on a pre-stress member, what all happens, that is the effect of the direct stresses Fx and Fy and tau v, which leads to the generation of principal stresses, which is F maximum and F minimum, which are obtained by this formula. So in the first part we will have analysis examples where Fx, Fy may be given or may be asked to find, or we have to find the maximum and minimum principal stresses. So problems of first category are a bit easy. So in the next lecture we will be starting with the problems for shear. Thank you.